Hello everyone. I hope you all are keeping good health and thanks for dropping by. And I would also like to thank the organizers for being able to organize the Beyond IIT conference this year amid such a difficult time. So I would like to speak about a concentration of measure result for non-catalytic decoupling via approximate unitary T designs. So the title looks kind of long, but all it means is that we want to prove a fundamental probability concentration result where we want to show that probability of a certain function is highly concentrated about its mean, or as we deviate away from the mean, the probability decays exponentially. In the process, we do not want to use any pre-shade entanglement, and we want to use approximate unitary T designs. This is joint work with Pranab Singh. So let us have a recall at what the decoupling theorem is. So decoupling is a strategy by which we can transform a particular mixed state, let's say on a bipartite subsystem AR, to a state which is very close to a product state. Now, it was shown by Dupuy that the process to do it, or the way to do this, was that you apply a Haar-random unitary only over the subsystem A, conjugate it with the input state rho AR, and then pass this through a quantum channel. So it was also generalized to the case when we do not need to consider the channel, but only consider a super operator which is completely positive. Okay, so the resultant state, so let's call the state as sigma BR as the output of this particular decoupling process. So since we have chosen Haar random unitary, the state sigma BR is random. If we take its Haar integration, it can be shown very easily that it is indeed equal to a state omega B tensor rho R, where omega B is equal to the super operator tau acting on a completely mixed state, or it is the reduced state of the choice state of the super operator tau. So Dupuy managed to show that if we look at the trace distance between the output of this decoupling process and the state omega b tensor rho r, and then if we take expectation over Haar measure, and if certain entropic conditions are met, then indeed this expectation is small enough. Or in other words, if certain entropic conditions are met, then we can indeed transform a particular state rho AR to a tensor product state within some approximate limits. So rigorously what this means. So let's say rho AR was our input state, then the function f, which we shall henceforth call as the decoupling function, is defined to be the trace distance between the state which is obtained as the output of the decoupling process and the state omega b tensor rho r. Now we want to find the expectation of this function when the unitary u is chosen randomly from Haar measure, and henceforth we shall call such unitary as the unitaries that can achieve decoupling or the decoupling unitary. Okay, so Dupuy has shown that the expectation of this function f, which is denoted by mu, is upper bounded by square root of 2 times minus sum of two entropic quantities, where the first entropy is the conditional relative entropy of system A given system R evaluated with respect to the input state rho AR, and the second entropic quantity is the conditional relative entropy of system A given system B evaluated with respect to the choice state of the super operator tau, which we are denoting as omega A prime B. Now, if indeed the entropies are such that this expectation or the upper bound of this expectation is small, then we can say that on an average, we have a decoupling result. So this is what we mean when we say that decoupling on an expectation. But in order to analyze how sharply the function f is concentrated about this particular mean mu, we need to take a step further and evaluate the probability that the function f is greater than or equal to mu plus delta. And it will be best if we can show that this is indeed exponential, or we can show that as we deviate away from mean, the probability drops exponentially. So this probability we shall refer to as the tail probability, and as the title suggests, this particular phenomena where we show that f is exponentially concentrated about the mean mu, we refer to this as the measure concentration phenomena for the decoupling, because the underlying function is the decoupling function. Okay, but this is not what we do. This is the slide about Dupuy. So he has managed to show that when the unitary comes from Haar measure, then indeed the function f is concentrated exponentially about its mean mu. And this was done via the so-called Levy lemma. So Levy lemma says that if you have a function f which is Lipschitz and the underlying randomness comes from Haar measure, then indeed this function f is exponentially concentrated about its mean mu. Okay, so in order to come up with this particular concentration result, The challenging task was to evaluate the Lipschitz constant, and it turned out to be twice of the diamond norm of the superoperator tau times square root of the operator norm of the state rho A, which is nothing but the reduced state of the input over system A. Now, since Haar random unitaries are not efficient to implement, Seher et al. Considered the case that can we prove such a decoupling theorem when the unitaries are efficient, or in other words, they choose the unitaries coming from a delta approximate 2 design. And as a side note for the experts, these approximate 2 designs can be constructed efficiently via the so-called Clifford circuits. Okay, so coming back. So Seher et al. Managed to show that the expectation of this decoupling function f when unitaries are coming from these approximate 2 design is indeed very similar to that of the Haar random expectation. Okay, now this expectation as shown here, it has some additional multiplicative and additive terms. So that is the additive terms are due to replacing Haar random unitaries via approximate 2 designs, and also the multiplicative term is because we're using approximate designs and not the exact designs. Okay, so more on this later. But let's recall the definition of the smoothed version of the Renyi 2 entropy. So it's nothing but maximum over all the matrices rho prime, which are positive, and they lie in an epsilon ball of rho, where the epsilon ball is defined either with respect to the trace distance or the purified distance of the conditional Renyi 2 entropy evaluated with respect to rho prime. Okay, and why we want a result with respect to the smoothed entropies, it is because it is instructive to evaluate any protocol in information theory with respect to the smoothed entropies, because a pedagogical step in information theory is to evaluate the asymptotic ideal limit because it is of engineering importance. So it is well known that the smoothed version of the conditional Renyi 2 entropy, it converges to the conditional Shannon entropy. Now, the theme here is de-randomization. So what do we mean by this? So we know that Haar random unitaries are inefficient to implement. They use exponential number of resources, and the resource for us mainly here is the random bits. So one possible approach for efficient implementation, or to take a step towards efficient implementation, to say for the least, we want to replace a Haar random unitary by a unitary chosen from an approximate unitary T design. Now what's a unitary T design? So first of all, you consider a set of finite number of unitaries as opposed to the entire unitary group. Now define a uniform measure on these finite set of unitaries. Next, consider a function which is polynomial in the entries of U. So it is a function which is defined from the set of unitaries to set of all complex numbers such that the function f is polynomial in the entries of U. Now, if we calculate the moments up to order t of this function f with respect to this uniform measure, it mimics the moments with respect to the Haar measure. If the moments are exactly equal, we say they are exact designs. But we do not have efficient construction of exact designs when the value of t is strictly bigger than 2. But we have efficient construction of the designs when we consider moments within an approximate parameter of the Haar, or within an approximate factor, which is here the additive approximation of the Haar measure. Okay, so all I mean to say is that the expectation of the moments up till order t with respect to this uniform measure is some epsilon by dt close to the moments with respect to the Haar measure up till order t. And we have efficient construction for these epsilon approximate unitary t designs when the value of t is polynomial in the log of dimension of the unitary. And if we want to replace a Haar random unitary via unitary coming from these approximate t designs, we need to make sure that we have the following two conditions. First of all, the function f should be polynomial, which just comes from the definition of designs. And the second thing is we want a Haar concentration for the function f, which is generally given by Levy lemma. Now this step is important because if we have a Haar concentration result for the function f, we can evaluate the Haar moments of the function f up till order t. Then bring in the definition of approximate designs and replace the moments with respect to Haar via the moments with respect to t designs. And then we can apply Markov inequality to get a probability result for the function f when the unitaries are coming from approximate designs. So this technique was given by Richard Lowe and known as last deviation bound for k designs. So we shall rely on this technique to replace our Haar random unitaries via unitaries from t designs. Okay, so this is what we want to prove, that we want to prove a similar concentration theorem for decoupling using design similar to that of the Haar. So remember what Dupuy had managed to prove, that the function f is indeed concentrated about its mean and the concentration is exponentially sharp. So we want to prove a similar result for designs. Now what is known in this direction? So a very important corollary of the decoupling is known as fully quantum sleep involved. So this is the corollary which is applied everywhere in Shannon theory. So the setting is as follows, that the system A is equal to the tensor product of two subsystems A1 and A2. And the super operator tau, it maps the system A to the subsystem A1 by just tracing out the subsystem A2. So it is indeed a CPTP operator. Okay. So Nakata et al. Managed to show that we have a concentration result in the fully quantum sleep involved setting when the unitaries are coming not from R, but which are diagonal in Pauli X and C basis. Now these unitaries are important in many body physics or in studying chaotic systems. Okay, but unfortunately, these unitaries are not efficient for technical reasons, which we are not discussing here right now. And also the concentration is weak. Nevertheless, it is an important result. Another result in this direction was an efficient decoupling theorem, but using pre-shear entanglement. So this was proven by Anshu and Jain. So in our work, we want to come up with a concentration result for the decoupling when there is no pre-shear entanglement and unitaries are efficient, or they use at least less number of random bits than Nakata et al.'s work and also Dupuy's work, which was using hard random unitaries. So we can say that this work is a step towards fully de-randomization. And I would like to remark here that in the fully quantum sleep involved setting, if the value of the output dimension of the super operator, which is the dimension of A1, is equal to polylog dimension A2. So A2 is the subsystem which was traced out. Then we indeed have efficient unitaries that achieve exponential concentration. But in general, T is larger than what is known to be efficiently implementable. But nevertheless, we save on the random bits. So moving on. So now let us come to the main technical section. So what do we want to prove? So we want to come up with the tail probability of the function f when the unitaries are coming from an approximate design. So the first hurdle is that the function f is defined in terms of trace distance. So it is not polynomial. Since it is not a polynomial, we cannot naively replace a R random unitary by a unitary coming from an approximate design. So what do we do? So we appeal to what was done in the previous works, which is the weighted Cauchy-Schwarz inequality. So which is one thing that always helps when you are stuck. Okay. So what is weighted Cauchy-Schwarz inequality? It just says that Schatten-1 norm or the trace norm of a particular operator M is upper bounded by the Schatten-2 norm or the Frobenius norm of a related operator M tilde. Now M tilde is obtained by conjugating M with a positive semi-definite operator sigma to the minus 1/4. So henceforth we shall call this sigma weighting operator. Okay. So now notice that if we choose the weighting operator sigma correctly, then indeed we get that the 2 norm of M tilde is equal to square root of 2 to the minus conditional relative entropy. And it is this particular magical bound that showed up in all the previous work in getting the expectation of the function f, which can also be thought of as the error between the actual output that we are getting from the decoupling process and the tensor product state. And it is given in terms of the conditional relative entropy. Okay, but just by using this Cauchy-Schwarz inequality or the weighted Cauchy-Schwarz inequality, our work is not finished. So what we need to do further? Okay, so further what we need to do is we need to upper bound f with g, as I mentioned earlier, where g will be defined in terms of the Schatten-2 norm. Now, if you look at the square of the Schatten-2 norm, which is the function g square in this case, then it is indeed a balanced degree 2 polynomial in the entries of U. So there's hope of applying a Lowe's technique and coming up with concentration for the function f, if we can upper bound f with g square. So, okay, but let us move to the concerns. So first of all, we need to do a Lipschitz analysis, or we need to find a Lipschitz constant of the function g, which is a non-trivial task. So this will be the first takeaway when you read the paper, that how do you come up with the Lipschitz constant of the function g? So in order to do this, we really have to look at the geometric behavior of the super operator tau by appealing to its time spring dilation. Then the second challenge is, once we have calculated the Lipschitz constant of the function g, Levy lemma gives us an exponential higher concentration for g for free. But then we have to prove an exponential concentration or a similar concentration for a function g square. Now this looks trivial, but is indeed a particular challenging task in this work. And the second hurdle is, so far we have said that, okay, upper bound f by g look at G square, and somehow try to find out a concentration result for G square. But how do we define G? So in order to define G in such a way that we have the expectation of the function G and ultimately the concentration of the function G about its mean, or the function G square about its mean, in terms of smooth entropic quantities, we have to perturb the superoperator tau with tau hat such that tau and tau hat are close in diamond now. Okay, because this is a superoperator now. So one thing to notice in weighted Cauchy-Schwarz is that the weighting operator sigma is conjugated with respect to a particular state, and this state would generally lie in the range space of the superoperator tau. Okay, so what we are doing is we are multiplying the inverse of the weighting operator with a particular state which lies in the range space of tau. So in order to avoid the inverse being undefined or the inverse not being well defined, we have to make sure that the support or the range of the superoperator tau is indeed contained in the weighting operator. Okay, so this is also one of the challenge, and it should be contained in such a way that when we evaluate the IID limit or the asymptotic IID limit, we indeed are able to recover the Shannon entropic quantity or the analogous Shannon entropic quantity. So this makes the choice of the weighting operator challenging. This makes the perturbation challenging, and this makes the overall analysis very challenging. And at this point of time, I think it is right to mention that the decoupling is essentially a one-shot result, because in proving decoupling, all we are doing is using the superoperator once, and hence using the choice state of the superoperator once, and also using the input operator once. Okay, but for engineering reasons, we would really like to see that what is the asymptotic IID limit, and is the error, or is the rate, or is the distance between the two states on average or with high probability in IID, does it have any operational interpretation as well? So if we have Shannon entropies, we can come up with an operational interpretation to it. Okay, so considering all these things, we define the function G as follows, which was a long halted task till now. So the function G is defined as, first of all, the distance that we get from Schatten-2 norm or the Frobenius norm of the state that we obtain as the output of a decoupling process when the superoperator tau is replaced by the superoperator tau hat, such that tau and tau hat are close in diamond now, to a particular product state, which is omega hat, which is nothing but the state obtained by passing completely mixed state through tau hat. And rho tilde prime AR is so chosen such that the 2 norm of rho tilde prime AR is indeed equal to square root of 2 to the minus the smoothed version of the conditional Renyi-2 entropy. Now, in this process, since we have to make sure that the support of tau is contained in the support of the weighting operator, and we have to perturb tau with tau hat. So this calls on for defining a new smooth entropic quantity. So here, let us call that as the smooth max entropy, or in this work, we shall call a new entropic quantity as smoothed max entropy, which is defined with respect to the state omega b, which is the marginal of the choice state of the superoperator tau, not tau hat, of the superoperator tau. So the smoothed max entropy, which we are denoting as h prime max epsilon of the system B evaluated with respect to the state omega b, is defined as log of operator norm of a particular smoothed version inverse of the state omega b. So the smoothed version of the state omega b, which we are denoting as omega double prime epsilon b, is obtained or is defined as a positive semi-definite matrix, which is obtained by zeroing out those smallest eigenvalues of omega b that sum up to less than epsilon. Okay, so this is one of the technical criteria that one has to keep in mind, because this will show up in the analysis of the Lipschitz constant, and we want to make sure that the Lipschitz constant is not too high so that the concentration that we get ultimately is not exponential. And also we have to define this in such a way that when we want to prove the asymptotic IID result, okay, so that we want to prove by looking at the eigenvalues of the n-fold product of the states and try to come up with some typicality result, as in the case of traditional information theory, and then see to it that we are able to come up with either the convergence or some appropriate bound on these smooth quantities in terms of their Shannon analogs. So all these considerations indeed tells us that the Lipschitz constant of the function g is dependent on these newly defined smoothed max entropy and the smoothed version of the vanilla conditional relative entropy of the system A with respect to the system R, evaluated with respect to the state rho AR, which was the input state. Okay, so the next step, we want to find out how the function f is concentrated about its mean. Okay, so then we want to, in turn, in the hindsight, evaluate the expectation of the function g. Okay, so now, since again we have perturbed tau with tau hat, and we have to choose the weighting operator very carefully, we have to reevaluate the expectation of the function g. And in this evaluation, we come up with a newly defined smoothed conditional relative entropy, which we are denoting as H2 prime epsilon delta. So here epsilon and delta are two controlling parameters of A given B evaluated with respect to the choice state of the superoperator tau. So this is defined to be minus 2 times log of minimum of the Schatten 2 norm of I tensor a particular smoothed version of the marginal state omega b to the minus 1/4 conjugated with the state eta ab. Now, this is very similar to the definition of the vanilla version of the smoothed conditional relative entropy, with the difference being that the state eta in the vanilla version just needs to be an epsilon wall of this original state omega. Here, along with this, we want to make sure that we have another operator inequality, which is that eta lies between the states 0 and omega. And furthermore, in order to evaluate the IID limits and make sure that that is in terms of the analogous Shannon entropic quantity, we want that all the vectors in the support of the state eta, they should have a good enough projection on the smoothed version of the marginal state omega b. Okay, so what is the smoothed version of this marginal omega b? This we are denoting by omega triple prime epsilon delta. So this is the positive semi-definite matrix, which is obtained by zeroing out those eigenvalues of omega b that are at most 2 to the minus 1 plus delta h max prime epsilon of b. Okay, so this is just there to make sure that we have some properties like that of quantum or classical typicality, so that we can show that in the asymptotic IID regime, H2 prime epsilon delta is bounded appropriately by H of A given B, which is just the conditional Shannon entropy. So now, putting all the parts of the proof together, we can outline the proof in the following way. So from f, we go to the function g by perturbing tau by tau hat and applying weighted coefficients. Let's call that as a step 0. Then we apply Levy lemma to obtain exponential higher concentration for the function g minus mu. Now, using this, we prove an exponential higher concentration result for the function g square minus mu square. Again, remember that the unitary u is coming from higher measure at this step. Then we obtain the 2mth moment of the function g square minus mu square with respect to higher measure again. Now we bring in the definition of T design, replace the unitary via unitary coming from an approximate T design, and evaluate the moment subtle order T of the function g square minus mu square. Here the value of T is chosen to be 2m, and then apply Markov's inequality to get a probability result. In other words, we are applying the Lowe's technique now. So the last step of the Lowe's technique, where we apply the Markov's inequality and replace the moments of R with respect to the moments from designs, gives us the value of T for T design and also the approximate parameter. So the approximation parameter is chosen so that the moments are more or less equal with respect to R and design. And the value of T and the moments, okay, both of these things are chosen such that the concentration that we get is exponential. Now, using standard manipulations, we can find out the tail probability of the function f, given that now we have the tail probability of the function g square. And finally, we evaluate the appropriate asymptotic IID bounds. So we do not show the exact value of the limits, as we do not need it for this particular work, but that can be taken as a work for future, the asymptotic IID bounds on the newly defined entropic quantities. So this is the following result in a nutshell, that the function f is the decoupling function, which is nothing but just a trace distance between the state that is the output of the decoupling process minus the Haar integration of this output state, which is a tensor product state omega b tensor rho r. Omega a prime, we remember, is the choice state of the superoperator tau. So we managed to show that the expectation of this function f, when the unitaries u are coming from an approximate design, they are very similar to that of the Haar expectation of the function f, with the difference that the smoothed entropy of A given B is now replaced by our newer version of the smoothed conditional relative entropy with two controlling parameters epsilon and delta. Okay, and at this point, or it would have been better if I would have mentioned this point earlier, by all these considerations, the weighting matrix that we get, that is indeed equal to this new smoothed version of omega epsilon delta triple prime B. Okay, so this is the weighting matrix that will show up in the analysis, or this is the weighting matrix that will give us the particular expectation value and the concentration that we have. Okay, and notice the connection of this weighting matrix with respect to the smoothed max entropic quantity. Okay, so this was a slight digression. Okay, but nevertheless, it was necessary to mention here. Otherwise, it would have remained a surprise that what's the weighting operator that we are getting in weighted Cauchy-Schwarz. So sorry, I should have mentioned that earlier, but I hope it's clear. Then, as a second step, we are then able to obtain by appealing to Lowe's technique the concentration of the function f or the tail probability of the function f, and we indeed managed to show that the tail of the function f or the right-sided tail of the function f it decays exponentially. With the decay of the tail is controlled by the parameter a, which is a function of the dimension of the system on which the unitary is applied, which in this case is a, times the max, the newly defined smoothed max entropic quantity, and the vanilla conditional relative entropy with its smoothed version. Okay, and the value of t that we get is a function of this tail decay parameter a times the deviation from the mean, which is kappa square. And further, we show that the smoothed max entropic quantity is upper bounded by its Shannon analog, which is just the Shannon entropy of B evaluated with respect to the state omega B, and the newly defined smoothed conditional relative entropy of A given B is lower bounded by its Shannon analog, which is just the Shannon entropy of system A given system B evaluated with respect to the state omega AB, which is nothing but just the choice state of the superoperator tau. Okay, now why do we care about decoupling? Okay, so we care about such theorems because they have wide range of applications, at least in quantum Shannon theory. So in quantum Shannon theory, they show up everywhere in source coding and channel coding problems. So one such application that we saw was the so-called fully quantum sleep-involved setting. Okay, and further, the main crux that is to be taken from decoupling in the coding problems in information theory are that if one can produce an encoder by decoupling, then it turns out that a suitable decoder is automatically guaranteed by appealing to Ullmann's theorem. So this just reduces our work to half in just coming up with a particular encoder. Now, we need the result of decoupling all the way up to concentration when we are considering another phenomenon in quantum thermodynamics known as relative thermalization. So in a nutshell, what is relative thermalization? So suppose we want to prepare an entangled state over the system S with respect to a reference R. Now, we just cannot inhibit the interaction of the environment E. So let's say we have a state rho omega R, where omega is a subspace of S tensor E, and this subspace is determined by some physical constraint, let's say total energy. So the global state is rho omega R. So now we want to apply a decoupling unitary on the state omega, or on the subsystem omega. Okay, but if we look at the reduced state by tracing out the environment from the state rho omega R, let's say that is the state rho SR. So it is observed that if the state rho omega R is allowed to evolve, then it spontaneously decouples into a state pi S tensor rho R. So this is the definition. So this is what we mean when we say that a system S is delta thermalized relative to the system R, meaning that the state rho SR is delta close to the state pi S tensor rho R in trace distance. Now remember here pi S is just not the completely mixed state, but it is the completely mixed state over a particular subspace. Okay, so this is what I want to draw your attention towards. And also another thing to note is that this is very similar to the fully quantum sleep-involved setting, with the super operator being trace out of E. There the super operator was trace out of A2, and the unitary is applied on the subsystem omega. Now, why do we need a probability concentration result? That is because the exponent in the tail probability of decoupling, it gives the fraction of unitaries that achieve delta relative thermalization. So this was important. So we wanted to find out what fraction of unitaries can achieve relative thermalization when the nature is allowed to evolve unitarily, or when the nature evolves unitarily. And we want to really look at that we really want to look at the question, is nature indeed evolving in a hard random way and not in a computationally efficient manner? but we are able to show that if nature evolves in a computationally efficient manner, which we expect the condition to be, then indeed we see one of the natural phenomenon, which is relative thermalization. Now, furthermore, we are able to draw contrast of our result with the pre-existing result. In other words, so our concentration bound is midway between Dupuy's bound, which was better than ours, and Nakata et al.'s bound, which, as we mentioned, is weaker than us when we assume some reasonable value of the underlying parameters. And these parameters are the deviation from mean kappa, then certain reasonable value of the smooth version of the conditional relative entropy, which shows up in the expectation, and the conditional smoothed version of the conditional relative entropy of omega given r, and the mean entropy of the source, or so this is one way to look at it, or the smooth mean entropy of the state rho omega. Okay, and we are able to show, so what is our advantage? So our work in a particular sense is stronger than the previous works, and the sense that I'm talking about is that the number of random bits that we need to implement our unitaries are much lesser than that of Nakata et al. And Dupuy et al. Because omega is a system of interest, which is a subspace of S tensori, and generally the system of interest S will have a dimension which is much smaller than omega. So we need unitaries coming from an approximate polymodus times log mod omega design, whereas Dupuy needs higher random unitaries, and Nakata et al.'s work used unitaries which are diagonal in X and Z basis. Okay, and moreover, our unitaries have efficient implementation when the value of S is polylog mod omega. So this is what we remarked when we mentioned about fully quantum sleep involved setting. So in summary, we've proven a really fundamental result where we want to come up with the probability of a particular decoupling function and prove that such a probability is exponentially high when we want to see the concentration of the function f about its mean mu. Or in other words, we are able to show that the tail decays exponentially. So this fundamental or simple looking expression does answers one of the question that indeed the nature can do something computationally efficient, which we hope it does. Furthermore, our new entropic quantity, which was the newly defined smoothed conditional Rennie-2 entropy, it has already found application in one of the works which was presented in this particular Beyond IID, which was finding the one-shot capacity of a fully quantum multiple access channel, which was presented by my colleague Sayantan. So we hope that there will be a lot more applications coming up from these kind of results. And also it will be interesting in its own right to look at the proof techniques. It's not that they are very non-trivial, but it indeed is a way to look at things from a geometrical point of view. Okay. So thank you very much for your attention, and I'll be more than happy to take any comments or questions on this. And if anyone wants to extend this work in any particular direction that they seem useful, I'm still hunting for the applications. Thank you very much.